Okay, welcome to our first lecture on electrostatic charge and electrostatic force. So we step away from basic mechanics now and are starting to take a look at one of the other fundamental forces, what we call the electrostatic force. The electrostatic force is all around us. We make use of electricity on a continual basis, not only in our electronic devices and household appliances, but in every signal that propagates through our nervous system. Without the electric force, chemistry could not exist. The electric force is responsible for every molecular interaction. The electric force is responsible for atoms. So we can look at pictures we can see lightning, we can do little tricks with balloons, and those give us an illustration of the electrostatic force. But this truly is a very, very fundamental component of our existence. So let's sort of bring this up from the ground up. The ancient Greeks first identified that under certain circumstances, materials could attract or repel. Now, the ancient Greeks first identified magnetism as well. We'll talk about that, but this was different than that. What they noticed is that typically they would bring materials together, and they could rub these materials together, and then they could exert forces on things. So you could attract or repel little bits of leaves, a stream of water. I mean, like a falling trickle of water. Um, and what they identified was that basically there are two different possible interactions. Either you could generate a repulsive force or you could generate an attractive force, depending on exactly what you did. And so what they managed to figure out was that this had to arise from two different flavors, two different types of things. It seems kind of funny to use the word flavor here, but just two different species of matter. When the same flavor was brought together, the materials would repel one another. When the opposite flavors, the two representative of the different flavors, are brought together, the materials would attract one another. And that was responsible for all the attraction repulsion that was observed. Now, we don't usually call that flavor outside of the physics classroom. We call it charge. Electric charge, or just charge usually for short. And we name those different charges as positive and negative. And the names don't really mean anything. They're just two names for these charges. We could call it Alice and Bob, frankly. But the nice thing about positive and negative is that it does allow us a little bit of mathematical simplicity. So we're going to use those names to help as not just names, but as mathematical tools. In normal matter, charges are represented in protons. Positive charges are carried in protons. Negative charges are carried in electrons. These are by no means the only types of charged particles. But the other types of charged particles that we run into are much harder to come into contact with. There are circumstances in kind of the everyday world where we can see that. Typically, when cosmic rays disintegrate in the upper atmosphere, they can generate a bunch of other different interesting charged particles. You're not really going to come into contact with that, but they're there. So what's interesting about these charges is that the effects of charges are cumulative. We'll talk a little bit more about this cumulative nature in a little bit. Multiple positive charges have a greater effect than individual charges. And so their effects add up, but they also subtract from one another. So if we have a bunch of positive charges, a bunch of negative charges, we put them in the same place, they essentially cancel each other out. And again, we'll talk a little bit more about how that works in a little bit here. Which, interestingly enough, as what that's going to do, if you have equal numbers of charges, those flavors, those positive and negative charges, will cancel each other out. And if you have exactly equal numbers of charges, that will essentially leave the bulk material with zero charge. And as we're going to see, the interaction that these charges experience is based on the amount of charge that there is. So when we have a large object with zero total charge, then essentially it does not participate in that force. We'll talk about that again as we go on. Electrostatics is a study of forces between charges that are essentially stationary or not moving rapidly or not moving continually. When we have a flow of charge, a river of charge, we'll call that a current. We're going to discuss that a little bit later on. We identify a couple of different types of materials. We can sort of take all the materials that we see and sort of divide it up into two categories. It's a little bit fuzzier than that, particularly right down the middle, but effectively we have two different types of charges, two different types of materials rather. So conductors are materials that allow charges to move easily. So we typically think of metals as the most obvious conductor. Metals allow charges to move quite simply. Essentially, if we have a bulk material, when the metal atoms bond together, they basically donate one or two electrons that are sort of free to slosh around that metal. They can move fairly easily through that material. And interestingly enough, when we do have charges in a metal that are not bound to an atom, that can move around, they basically, in general, they sort of move around there kind of like molecules of a gas do in a big room. They spread out. Now, they spread out a little bit differently. We saw last semester that when particles in a gas, in a room, for example, spread out, they spread out really uniformly from one another, which causes them to sort of occupy all space uniformly. And they do that because there's so many more ways to sort of spread out from one another than there are to all be grouped in one place. So there's that entropy thing coming back again. In a conductor, the charged particles tend to spread out around as far as they can possibly get from one another. And the way that they do that is spread to the boundaries of that volume. So if you take a look at that little cartoon down here at the bottom of the page, you'll note that if we put some charge on a metal sphere, at first, we've got a bunch of this negative charge sitting at this one spot, but that negative charge will spread out all around that sphere. It won't spread throughout the middle. The interior, the bulk of the interior surface of that sphere will essentially be charge free. All those excess charges will sit on the outside. Now, of course, keep in mind that this whole sphere is made up of charges, protons and electrons, but those are bound up in the atoms, and they're not free to move around. What we're talking about here is when we have excess charges that can move around, and they will move around in a conductor. Now, our other type of material is a dielectric. And dielectrics are also made up of charges, but the nature of dielectrics is that the charges cannot move easily through those dielectrics. Now, again, so one main difference is those materials do not donate electrons to be able to slosh around the bulk. But even then, even without that, if we apply extra charges to that dielectric, they will just essentially sit on the surface where we put them, and they won't really move around very easily. We'll talk a little bit more about dielectrics later. We'll note here that a dielectric is sort of the technical name for the material that you might call an insulator. Now, what's interesting, we'll note here, is that in a dielectric, each individual molecule, of course, has positive and negative charges, and we might think of them as sort of being randomly distributed, but there are circumstances, particularly when we stick charges on around them like this, so we can get them all to align. Well, again, we'll talk about this a little bit more later on when we dig into talking about the electric field some more. But for right now, understand that we have materials that can allow charges to move easily, to move freely through them, and we have materials for which the charges do not move easily, our dielectrics. Now, the way that the Greeks managed to identify these charges, and in fact, one of the ways that we interact with the electric field on a regular basis is essentially amounts to through the process of rubbing. We call this a triboelectric effect. Tribo in the Greek means to rub, and the idea here is that when you take certain materials and you bring them into contact with them, maybe you rub them back and forth a little bit, or you just bring them into contact and you peel them apart from one another. Certain materials like to accept electrons, and certain materials like to donate electrons. And we can rank these materials in this thing we call the triboelectric series. So if you look at the plot over on, or the little graphic over here on the right, materials to the top of the triboelectric series, the positive side, they want to donate electrons. So if you take a neutral atom with equal numbers of protons and electrons, and one of these materials donates an electron to something else, that material now is less negative than it should be to remain neutral, which means it's going to carry a positive charge overall. Materials lower down on this list like to accept electrons. And so they will grab extra electrons, and therefore, because they've got more electrons than they would need to be neutral, they will carry a net negative charge. And so what happens is you take two of these materials and you rub them together. So let's say something like you take a natural rubber, and you rub that natural rubber up against some wool or some nylon. Nylon would be even better. So nylon and natural wool, when you rub those two things together, while in the beginning those things, if you take a look at this little cartoon picture here on the bottom left, in the beginning each one is neutral. As you rub them together, one of them will become much more negative, one of them will become much more positive. Now this is a cartoon. You're not going to transfer all the negative charges in one place and all the positive charges to another, but the effect is you have more negative charges on one than you did originally, more positive charges on the other than you did originally. So then you develop this electric charge, or the separation of charges. And that separation of charges is what the ancient Greeks observed when they first started seeing this thing that they labeled as this electric effect. Now, what's really kind of interesting about this, incidentally, by the way, that effect of rubber on nylon is what happens when you rub when you are walking across a carpet in your trainers, in your sneakers, and then you touch a doorknob. As you walk across the carpet, you are bringing that rubber into contact with the nylon or the other polymer in the carpet, and you are building up an excess of charge. And in fact, you can build up to 30,000 volts per centimeter of electric potential. We'll talk more about that again here later on. That way, to the point that when you go and touch a doorknob, you have so much charge on you that it will jump across the gap between your finger and the doorknob just before contact, and that will cause that little bit of shock. Or when you touch someone else that way. When you rub a balloon on your hair and you get your hair to stand up, like in that picture over here at the beginning, that's the same thing that's happening there. Human hair against the latex of the balloon. Now, what's interesting about this triboelectric series is it's not just that these things all charge positive and these things charge negative. You take any two of these materials and you rub them together, something is higher on the list than something else. And the one that's higher is going to tend to charge positive, one that's lower is going to tend to charge negative. So if you rub lead against cotton, the lead will charge positive and the cotton will charge negative, because lead likes to give up electrons more than the cotton does. Now, that will not give you a very large amount of charge to be transferred, because those things are so close together. And cotton doesn't really like to accept electrons. It would rather give electrons away. But lead likes to give electrons away even more. So that's what's taking place. And in fact, interestingly enough, we'll talk about this a little bit more later, that's essentially not entirely dissimilar from what's happening in a thunderhead, in a cumulonimbus cloud that's going to give rise to our lightning bolts over here. Now, one last little bit of trivia here for you is this. if you take, oh, I don't have it on this list, but if you take a piece of wool and you rub it against a piece of amber, you'll get the same effect. So amber, of course, you probably know is petrified tree sap. Has a beautiful amber color to it. That's why we call that color that name. And it's very strong. It has a very large triboelectric effect. And so this is one of the materials that the Greeks first noticed as possessing this. You take a piece, I can imagine what happened. They found a piece of amber, they polished it up because it was pretty. They rubbed it with a piece of cotton cloth, and that amber, which is way down here on the triboelectric series, developed a really strong electric charge, and it was able to zap. Get a little zap out of it when they polished it up, and then handed that piece of amber to somebody else to take a look at. And interestingly enough, the Greek word for amber is electron. So that whole word, electric, that root of electric force, electric field, electric charge is electron, which means amber. So there you go, a little fun piece of trivia. Okay. Now, charge, we can pile up lots and lots of charge in one place, but the very smallest amount of charge there is a smallest amount of charge that you can have. There is a discrete amount of charge, and we don't, with like a very, very small number of exceptions, you cannot break that smallest amount of charge up into any smaller bits. We say that the charge is discrete. We can't break it up beyond that smallest amount. So we call that very smallest amount of charge the elementary charge, hopefully for obvious reasons. Now, the elementary charge, E, is not an MKS unit. The MKS unit for charge is the Coulomb, named after Charles Augustin de Coulomb. But one elementary charge, which incidentally is the charge of a proton, or the charge on an electron, is equal to a very, very, very small number of coulombs, 1.602 times 10 to the negative 19th coulombs. 1 coulomb is a tremendously large amount of charge. So a single proton has a charge of plus E, plus 1 elementary charge. A single electron has a charge of minus E, minus 1 elementary charge. Now, that sets us up to be able to actually talk about this electric force. The electric force is described by something that we call Coulomb's law. And so we call it either the electrostatic force or we call it the Coulomb force. And I will use those two terms interchangeably through this class. If we have two charges labeled as Q1 and Q2, why do we use Q for charge? I don't know. I really have no earthly idea. If I think about it, I'll try to look that up and come up with an answer for you. Every now and again, I wonder about things like that. But Q is what we typically use for charge. Excuse me. So if we have two charges, Q1 and Q2, that are a distance r apart from one another, they will exert a force on each other that looks like the equation shown there as equation 2. The force of charge 2 acting on charge 1. So this is a force on 1 is equal to the product of the two charges, Q1 times 2Q2, divided by the square of the distance between them, r squared, multiplied by a proportionality constant k. And then we have that r hat unit vector. R hat, again, as a unit vector, it has a magnitude of 1. So if we just want to figure out the magnitude of the force, we can just drop that piece out entirely and talk about kq1, q2 over r squared. But if we want to talk about the force, the direction of the force, we need to introduce that r hat. And r hat is very simply just a unit vector that points from charge 2 to charge 1. So take a moment, draw that out in your notes. Take 2 points. I'm not drawing this for you. You get to draw this out. Draw 2 points. Label one 1 and the other one 2. R hat 2 to 1 points from 2 to 1. Now, let's look at what happens here. K is going to be a positive constant. You can see the value of it down there at the bottom of the screen, identified as equation 3. If Q1 and Q2 are both positive, then that ratio is positive because R squared is going to be positive. K is positive. So everything there is positive, which means that the force points, shown there on the left-hand side, points in the same direction as R2 to 1. So if both charges are positive, the force on 1 from 2 points from 2 to 1. Essentially, it points away from 2. It's a repulsive force. If Q1 and Q2 are both negative, then Q1 times Q2 is also a positive quantity. And we see the same picture again. The ratio Q1, Q2 over R squared is positive times K is positive, which means that the force on 1 due to 2 is parallel to R2 to 1. It points away from 2 towards 1. So that force on 1 is away from 2, directly opposite away from 2. Now, what happens if Q1 is positive and Q2 is negative? Then the product Q1 times Q2 is negative, which means that F2 to 1 points in the opposite direction as R2 1. It points from 1 towards 2. So it becomes an attractive force. And the other case, if Q1 is negative and Q2 is positive, or whichever way around I said that before, that will also give us an attractive force. So this encompasses those characteristics that we saw about equal or the same flavor being repulsive, the opposite flavor being attractive. Now, we'll note as well a few things. The greater the charges are, either charge or both charges together, the stronger the force is. The further apart those charges are, the greater R is, the smaller the force is. Now, I'm going to introduce one more little piece here. Talk a little bit more about that proportionality constant just a little bit. And this is just to give us a little flavor for what that proportionality constant means. That constant, K, holds some very important information. And really what it does is it tells us how easy it is for those two charges to affect one another. And it's a constant, but it's a constant for a given material. So that value that I list here, that 9 times 10 to the 9th newtons meter squared per coulomb squared, is the proportionality constant in a vacuum. But that might change if we are in something else. If we're looking at charges in air, it'll change a little bit. If we're looking at charges in water or in polyethylene or in copper, that K will change. And what we do is we introduce a new constant called the electric permittivity, and we write it as a Greek letter epsilon. That's that funny E thing there over here above equation 4. So the permittivity describes how easy it is to establish an electric field or for the electric force to act. And for reasons that come out of the mathematics, it's related to K through with the assistance of this 4 pi here. That's not terribly important to us right now, but essentially, in a vacuum, that epsilon takes the value of epsilon naught, and it's equal to 8.9 times 10 to the negative 12th coulomb squared per newton per meter squared. And sure enough, if you take 1 over the product of 4 times pi times this, you'll come up with this 9 times 10 to the 9th newtons meter squared per coulomb squared. And so if we introduce that equation 4, this representation of K, back into equation 2 for the Coulomb force, we'll get to equation 6 down here, where the force of 2 on 1 looks like 1 over 4 pi epsilon naught, Q1, Q2 over R squared, R hat 2 to 1. Same equation. Now we just can talk about the material in terms of the permittivity, electric permittivity epsilon. That's not going to be overly useful to us right now, but when we start talking about different materials, that's going to be very handy. All right, so let's take a look at an example, and I apologize, that header on this page should be an example. Let's just try calculating a force. So an electron and a proton and a hydrogen atom are separated by about 53 picometers. Oops, let's get that out of the way. About 53 times 10 to the negative 12 meters. So what I would like you to do, I would like you to try to calculate this. Let's go back over here. We want to make use of equation 2. And we'll just use that proportionality constant there, K, and calculate the magnitude of the force. So don't worry about R, but you should be able to tell me what the direction of that R is. Pause now and try to solve that yourself. When you're ready, go ahead and resume the video. All right, I'm going to assume that you're ready to go, or that you got stuck. So let's take a look and try. We're going to use Coulomb's law. We're going to ignore the direction. The sign, we'll just think about the sign because it's going to tell us whether or not the force is repulsive, if it's a positive sign, or attractive, it's a negative sign. So we pull out that equation 2, Coulomb's law, shown there in the top line. That's this guy right here. And you see I've stripped out all the magnitude stuff. There's no magnitude. I've stripped out all the direction. There's no vector sign here. There's no unit vector on the right-hand side. So we can drop K in. We drop in 1 elementary charge for a proton, positive elementary charge, negative elementary charge for the electron, divided by that distance, 53 times 10 to the negative 12th meters squared. We do need to be in MKS units. Very, very frequently, we'll talk about charge in terms of millicoulomb or microcoulomb or nanocoulomb. We need to be in coulomb in order for our equations to work. Always work in MKS units, please. So you throw that into your calculator, and you come up with a number that looks like about 82 times 10 to the negative 9th newtons, which is about 82 nanonewtons. We can certainly report our units in non-MKS units, but when we operate with them, we definitely want to be using MKS units. All right, so that was fun. Let's investigate this just a little bit further. This is sort of this very fundamental interaction between a proton and an electron in a hydrogen atom. This is the most ubiquitous material that we know of in the universe, the hydrogen is. So let's do another little calculation, because that looks like a very small amount of force, 82 nanonewtons. It's a small amount of charge, even if it is fairly close together. It's closer together, remember, the smaller the distances, the greater the force is. But this is a terribly small amount of charge. Let's put this into context by seeing what gravitational force these things exert on one another. Now, we talked a little bit about this form of the gravitational force back in the first semester. Now, we're not looking at how much gravitational force does the Earth exert on a proton or the Earth exert on an electron. We don't know how much gravitational force the two things exert on each other. And if you think back to the first term, we described this gravitational force, this universal law of gravity that Newton described. And the equation for that is shown here on the slide. Gravitational force is equal to this gravitational constant, big G, times the product of the masses divided by the distance between them squared. Now stop for just a moment before you do anything else. Take a look at that equation. If this didn't strike you before, look at it right now. There's our gravitational force. There's our Coulomb force. Look at it again. Gravitational force, Coulomb force. They look almost identical. We have a constant times a product of things divided by the square of the distance between them. That's not a coincidence. Now what's interesting about that is these two forces have nothing to do with one another. And yet they both behave this way. They have this inverse R squared dependence. All right, so let's do some quick calculations. You're going to remember, we did some calculations quickly one day with this back first semester. Here we're going to go ahead and we know that I'm going to remind you of G, 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared, mass of the proton listed there, mass of the electron. Go ahead and try to calculate that. Now, while you do that, I'm going to make a note here. Take a look at those masses of the proton and electron. That's really kind of interesting. The proton is about 1,000 times more massive, a little more than 1,000 times more massive than the electron. The electron is a tiny, tiny thing. Proton is very big in comparison, very massive in comparison. All right, so you throw that calculation in there, and you should see something like this. The gravitational force works out to about 3.62 times 10 to the negative 47th newtons. I'm not even going to try to put a prefix on that. Go back over here. 10 to the negative 9th newtons, 10 to the negative 47th newtons. Wow! Let's compare them. And in fact, what I'm going to do to compare them is I'm going to take a ratio of the Coulomb force, our electrostatic force, to the gravitational force. I'm just going to divide them left-hand side by left-hand side, right-hand side by right-hand side. So I have a ratio of forces. I'm going to come up with a unitless number, and it's going to tell me how strong the Coulomb force is compared to gravity. So, and this is between a proton and an electron. And what you might notice when you take a look at the top over here is that I'm going to have 1 over r squared in the numerator and a 1 over r squared in the denominator. Those things will cancel out. So once that does, I end up with this thing. And what's really cool about this, that means that this ratio is independent of distance. No matter where these things are, this ratio of forces will be the same. And I'm going to throw these values in here. And you're going to look at this and you're going to say, well, there's a couple of things going on here. As small as that charge is, the masses of these things is ever so much smaller. And our constants, the K constant for the electrostatic force is big. It's 10 to the 9th. And that G constant for gravity is small. It's 10 to the negative 11th. We end up with something like 10 to the negative 39th. 39 orders of magnitude. The electric force isn't 39 times stronger. It's 39 orders of magnitude stronger. This is 1,000 billion, 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 billion times greater. The electric force, the Coulomb force between a proton and electron, is 1,000 billion, 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 billion times greater than the gravitational force between these things. What's interesting is the way that physicists look at this is it's not that the electric force is strong, it's that gravity is tremendously weak, which seems a funny thing to say. It's incredibly weak. And in fact, one of our fundamental questions we have as physicists is, why is gravity so very weak? Mind you, we're glad that it is, but why is it? Now, I like to illustrate this fairly simply this way. Imagine that you're going to take, if you haven't tried this before, go find a balloon and do this. Take a balloon, blow it up, tie it off, rub it against your hair, stick it to the ceiling. You've probably done that, or you've seen it done. Think about what's happening right there. There's 2 forces acting on that balloon. The gravitational force is pulling down, and this electrostatic force between the balloon and the ceiling is pulling up. All that's acting on this balloon to pull it up is a bunch of charges in the ceiling, a bunch of charges in the balloon attracting one another. That's it. On the other hand, gravity, you have all of the mass of the Earth pulling on all the mass of the balloon. Now, all the mass of the balloon isn't much, but you have all the mass of the Earth pulling down on it from the other side. And that tiny amount of charge in the ceiling and in the balloon is sufficient to balance the entire Earth. That's kind of a surprising concept. I mean, we used to that. We've seen this trick before, but that's really what that means. And this is where it comes from, the fact that this number is so big. All right, so if the Coulomb force is so strong and everything's made up of charges, why do we not really interact with it? We don't feel this Coulomb attraction to other objects frequently. On the other hand, if the gravitational force is, this should say so weak. If the gravitational force is so weak, not strong, why do we notice this force so much? Why is it, if it's 39 orders of magnitude smaller, why do we notice? The answer ties back to one of those first statements I made on an early slide. Charges add up. And not only do charges add up, but different opposite charges subtract from one another. So if I have a lot of positive charges and a lot of negative charges together, they might end up to show very, very little charge. Or if I have exactly equal numbers, they may end up neutral. Well, come back here for a moment to our equation. That one. No, this will do. If I look at this equation, if one of these objects is neutral, then the Q here is going to look like 0. Which means that the force is going to look like 0. But mass, on the other hand, there is no negative mass. It's all positive. So we put lots of mass together, we just get more mass. So the gravitational force never cancels itself out. Mass never cancels itself out. So with all the charge we have in the Earth, the reason that the Coulomb force is not really observed are not observed in the way that we would think it might be is because we have equal numbers of charge. Every atom is equal amounts of charge, positive and negative. And so every little package, every little atom of stuff is neutral, almost every. All right. So what happens if we have multiple charges present? The Coulomb force, as we've described it, is a pairwise force. Every charge acts on every other charge. So what happens if we have a bunch of them? So take this picture over here on the right. I've got 4 charges, Q1, Q2, Q3, and in this other charge, Q0. So what is the total force on charge Q0? Well, the answer to this is actually pretty simple. We're going to have to be good friends of our trigonometry again. But that aside, it's going to be fairly straightforward because the total force experienced by charge 1 is equal to the sum of the pairwise forces from each other charge acting on that first charge. So if I've got n charges, the total force acting on 1 is equal to the force of 2 acting on 1, plus the force of 3 acting on 1, plus 4, 5, 6, up to however many we have. So we can just do a simple vector summation. These are vector sums, which means we're going to have to take components. We call this the principle of superposition, and it actually makes a very, very difficult job very, very easy because we can break it up into these individual little pairs. So let's try an example here. We're going to take 4 charges. We're going to arrange them in a square with sides of length 2.5 centimeters. The 2 charges in the top right and bottom left corners, visualize this, write this down, draw a picture, draw a box with charges in the corners. The top right and bottom left are positive charges, positive 3.0 times 10 to the negative 6 coulombs, 3 microcoulombs. The charges in the other 2 corners, the top left and bottom right, are negative 3 microcoulomb charges. What I want to know is, what force is exerted on the charge in the top right corner by the other 3 charges? All right, so first, start by drawing a good picture. Hopefully you've already done that. Carefully label all the distances between each charge, as well as the charge values themselves. Label everything you know. For the sake of simplicity, I don't want to write down positive, negative, 3 all these numbers. We're just going to label these charges. Q1, Q2, Q3, Q4. Let's do the top right is 1, the bottom right is 2. We'll just go around clockwise, 1, 2, 3, 4, so that the top left is number 4. We're going to pick a coordinate system. I'll take x positive to the... I'm sure I meant x positive to the right. I apologize about that. I should say x positive to the right, and y positive up. Now, we're going to calculate the pairwise force between each of these other 3 charges and the top right charge. The other charges will exert forces on each other as well. We don't care about those. Those aren't important to the problem. We're only looking at what the net force is on that top right charge. So here's my picture. I've labeled it, and I'm only going to use those Q1, Q2, Q3, Q4 terms in my equations because it's so much simpler that way. All right. So now we are going to have to pay attention to our directions. Okay, so the force that the Q2, the bottom right, exerts on the top right will look like KQ1, Q2 over R squared, R2 to 1. I know what Q1 and Q2 are. They're labeled there. Q1, Q2. I drew a good picture. So I just need to think about what my unit vector is. Well, my unit vector points from 2 to 1. It's got to point from 2 up to 1. So I already said that up was the positive y hat direction. So that R2 to 1 is just positive y hat. That's it. So F2 to 1 looks like K, Q1, Q2 over R squared times positive y hat. If I plug in my K value from that 9 times 10 to the 9th, newtons meter squared per coulomb squared, times my charges, positive 3 microcoulombs, negative 3 microcoulombs. Of course, I got to be in coulombs, not microcoulombs. Divided by the distance between them. I believe that was 2.5 centimeters. So 0.025 meters, quantity squared. I come up with something like negative 129.5 newtons in the y hat direction, which means that force points down, negative y hat. And it's labeled there, F12. And I'm going to go ahead and draw that on my picture. I'm going to repeat that trivially do the same thing for charge 4 acting on charge 1. Take a moment before you go any further and think about that. What should the direction R4 to 1 look like? It's got to point from 4 to 1, so that should be the positive x hat direction, because I said x hat is positive to the right, regardless of what the slide said. Now, so we can calculate that, and we're going to come up with the same number, 129.5 newtons, negative x hat, so it'll point toward the left. So now let's take a look at that 1-3 charge, the 1-3 pair. What force does 3 exert on 1? All right, this one's a little more interesting, but only a little bit more. So the distance between these is the length of the diagonal, and I can use a Pythagorean theorem if I need to. Call the side length A. So Pythagorean theorem says square this side and add it to the square of this side. So a squared plus a squared, take the square root of that, and that'll give me that distance. So a squared plus a squared is 2a squared. Take the square root is root 2a squared, or root 2 times a. So there's a length R13. It's about 40% bigger than a. So I can throw that a, my 2.5 centimeters, in there and multiply that by the square root of 2. There's my distance. All right, the direction vector is a little more interesting as well. So the direction vector, we can actually expand, and we can say that the direction vector is made up of something in the x hat direction plus something in the y hat direction. And what it's made up of is a component of an angle. So that angle, I didn't draw it in here, but the angle is the angle between that vector and the horizontal. So it's basically this vector. Obviously, I can't draw in here in the slide, but it's this angle. So x hat cosine theta plus y hat sine theta, where theta, in this case, since it's a square, that theta is 45 degrees. So we end up with cosine of 45 degrees is root 2 over 2. Sine of 45 degrees is also root 2 over 2. There's my unit vector. We can talk about that more in person if you want to try that out when I get back. All right, so we're just going to put everything together. The force on 1 is equal to the force on 2 plus the force on 3 plus the force on 4. I'm going to add those things up. So here's the force from 2 on 1, the force from 3 on 1, the force from 4 on 1. We're going to add those together. Here's the force from 2 on 1. Go back and check it. Here's a force from this is a force from 4 on 1, and this guy right down here, the x hat 45.7 newtons plus y hat 45.7 newtons, that's the force from 3 on 1. If I come back here, that's this. Now take a look at my drawing here. That's 64.7, the magnitude is 64.7 newtons. The x and y components are the same. They're both positive, so it's pointing off at that 45-degree angle directly away from 3. And it's a smaller vector. Why is it a smaller vector than these guys? Well, because it's further away, so the force is smaller. So all we need to do is add these things up. I'm going to add the x hat pieces together. I'm going to add the y hat pieces together. I'm going to get this. Minus 83.8 newtons, minus 83.8 newtons. I can come up with a magnitude for that. Square of the x component plus the square of the y component. And I'm going to come up with 118 newtons, 118.5 actually overall. I can find the direction of that by taking the tangent. Arctangent, the tangent of the angle is equal to Fy over Fx. So phi is equal to the arctangent of that is 45 degrees. So I can put these things back together. All right, so this is all we need to do. And in fact, you'll see in some of the problems that we're going to assign for homework, you're going to add some things up. We can also look at where to place a charge in order to get a zero total force, where to find an equilibrium position. We're going to stop there for today. We'll let you work on some problems, and we will start talking about the electric field next time. Thank you for your attention. If you have questions, please make sure you make a note of them so that you can ask me about them. I am going to open up a discussion page on Socrates, and hopefully I'll be able to try to answer questions that everybody can see there, and that will help further us along. Thank you for your attention, and we'll see you next time.